Welcome to another deep dive into the source material. We have a really fascinating fundamental problem to look at today.
We do. It is essentially about how to make decisions in a universe that actively resists certainty.
Right, exactly. And whether you are talking about the architecture of artificial intelligence or just, human cognition, any agent operating in the real world has to navigate an environment characterized by partial observability and non-determinism.
Which is a very technical way of saying you never have access to all the variables.
Yeah, you just don't. And even when you take a really deliberate action, the environment it can always introduce some chaotic variable that just alters the outcome completely.
So we are unpacking the mathematics of belief today, moving from rigid traditional logic to the fluid, high-dimensional space of probability theory.
It's a huge shift. And I want to welcome you, the learner, to this study session. Imagine you're sitting at the table with us because we're going to get into some really dense but incredibly cool concepts.
The shift from traditional propositional logic to probabilistic reasoning is it's essentially the boundary line between early fragile AI systems and the robust machine learning models we use today.
Because early symbolic AI tried to map the world using absolute truths.
Right. Exactly. But physical reality doesn't afford us absolute truths. Partial observability means our sensors, whether biological eyes or digital cameras, they only capture a low-dimensional projection of a high-dimensional reality.
You only see a slice of the world.
Right, and non-determinism means the transition function between states contains noise. If you want to build a system that actually survives in that kind of environment, rigid logic is a massive liability.
Let's use the automated taxi scenario from the source material to ground this for everyone.
That's a great starting point.
So imagine you are trying to catch a flight. You are programming an AI to get a passenger to the airport, which is 5 miles away. You instantiate what the text calls Plan A90.
Meaning leaving the house 90 minutes early and driving at a legal speed.
Right. In a deterministic, fully observable toy world, classical logic proves this plan succeeds. The math works perfectly.
It does, on paper.
But the moment you deploy that agent into the actual physical streets, classical logic just immediately breaks down.
Because classical logic requires absolute proof. You cannot logically guarantee the outcome of Plan A90 without an exhaustive list of preconditions.
A purely logical agent attempting to evaluate this plan is just forced to output a massive conditional statement.
It determines that Plan A90 succeeds if the car doesn't suffer mechanical failure, and the traffic is nominal, and the tires maintain traction.
And the bridge hasn't collapsed.
Or-
And a meteor doesn't strike the vehicle.
Exactly, and the airport hasn't been suddenly relocated due to a sinkhole?
You just end up in this infinite regression of edge cases. Okay, let's unpack this, because this specific failure mode is what early AI researchers called the qualification problem.
The qualification problem, yes.
To make a logical rule true in a real-world domain, you are forced to add an infinite list of qualifications. And it's the reason why good old-fashioned AI, the symbolic reasoning systems of the 1970s and 80s, they hit a brick wall when trying to navigate open environments.
Medical diagnosis illustrates the qualification problem perfectly. Let's look at the foundational architecture of an expert diagnostic system.
Oh, I see your backdrop has shifted. You've got a clinical setting back there now, like a doctor's examination room.
It frames the problem well, I think, because medicine is perhaps the ultimate high-stakes environment for decision-making under uncertainty.
It really is.
It is the ultimate test of the qualification problem. If we attempt to code a diagnostic system using propositional logic, we might start with a simple causal rule, something like cavity implies toothache.
Which, from a physiological standpoint, seems sound right.
You would think so. The decay reaches the dentin, it irritates the pulp, and that generates a pain signal.
But logically, the rule cavity implies toothache is completely false.
It is factually wrong.
A patient can have a massive cavity discovered on a routine X-ray without ever having felt a twinge of pain. The nerve might be dead, or their pain tolerance might be incredibly high, or maybe the decay just hasn't hit the right cluster of nerve endings yet.
So to save the logical rule, you have to augment the antecedent with every single biological qualification required for a cavity to generate pain.
Thread it out like cavity, Andy inactive nerve, Andy pain tolerance below threshold X, Andy no local anesthetics present implies toothache.
The source text points out 3 insurmountable barriers to this approach. The first is laziness, though I prefer to call it the computational cost of exhaustive enumeration.
Meaning it's just too much work.
Exactly. The sheer volume of labor required to document every exception makes it an impossible engineering task.
And even if we had unlimited engineering hours, so we just hired 1 million doctors to write out the rules, we hit the second barrier, which is theoretical ignorance.
Yes. Medical science doesn't actually possess a complete deterministic model of human biology.
We don't have the equation for exactly how every protein folds or how every single neurotransmitter fires in a specific patient's jaw.
We are trying to write absolute rules for a domain where our foundational theory is still full of massive holes.
Which brings us to the third barrier, practical ignorance. Let's assume we miraculously overcome the first two. We have a complete theory of biology, and an AI has successfully written out the billion-condition logical rule.
It still fails in practice.
Right, because we can't run every necessary test on the patient sitting in the chair. We don't have their complete genome mapped in real time, or their moment-to-moment metabolic rate, or a live map of their neural pathways.
You synthesize laziness, theoretical ignorance, and practical ignorance, and you realize absolute logic is just a dead end.
And it's not just about medicine. If you are building an algorithmic trading model, the rule-strong earnings report implies stock price goes up is logically false.
Or if you're predicting weather, high humidity implies rain is false.
In any complex judgmental domain law, business, dating, gardening, we are forced to abandon binary truth. We have to operate entirely in the realm of degrees of belief.
Which forces a fundamental pivot in how we design agents. If we accept that an agent can never logically guarantee a successful outcome, how do we define a rational decision?
We have to introduce a framework that evaluates the desirability of different uncertain futures.
This brings us to utility theory.
Specifically, the principle of maximum expected utility, or MEU. The text defines a rational agent as one that chooses the action yielding the highest expected utility, averaged over all possible outcomes.
Essentially, decision theory is probability theory plus utility theory.
To go back to our taxi, Plan A90 might only offer a 97% probability of reaching the airport on time. But if the utility of making the flight is extremely high,
and the negative utility of missing it is devastating,
right, then MEU dictates that taking the 97% gamble is a rational choice over, say, a plan that only offers a 50% chance.
And we should look at Plan A1440 from the text?
Oh yeah, leaving 24 hours in advance.
Right. Leaving a full day early essentially guarantees you make the flight. The probability of success approaches 100%.
But the utility of hanging around an airport terminal for a whole day, eating awful airport food and sleeping on the floor, makes it an irrational choice for most people.
We should clarify what utility actually means in this mathematical context. It is a strictly internal metric. It represents the desirability of a world state to the specific agent.
It's just a function that maps a state onto a real number. But this is where I struggle a bit with the strict textbook definition of utility because it feels incredibly subjective.
It is entirely subjective.
Like the text uses an example where choosing jalapeno bubblegum ice cream over chocolate chip is considered rational as long as the agent's internal utility function values the jalapeno flavor more.
Preferring jalapeno bubblegum ice cream is definitely odd, but under the math, it is not irrational. Utility can account for typical, perverse, or even completely altruistic preferences.
It's funny because it justifies almost any behavior. If your utility function just highly values doing something incredibly difficult or annoying, then choosing the hard path is mathematically rational.
The math doesn't judge the preference. It only judges whether your actions are consistent with pursuing that preference given the probabilities.
Speaking of probabilities, to even calculate expected utility, we need to understand those underlying numbers. How do we quantify these degrees of belief?
We need to look at the basic language of probability. We have to establish the sample space, denoted by the Greek letter omega,
which is the set of all possible, mutually exclusive, and exhaustive worlds. The little omegas.
Exactly. And we assume anyone listening understands the basic axioms here, that probabilities must sit between 0 and 1, and the sum of all mutually exclusive possible worlds must equal exactly 1.
But what's far more interesting here is the philosophical distinction the text makes regarding what these probabilities actually represent. It separates our epistemological commitments from our ontological commitments.
This is a crucial distinction. Ontologically, concerning what the world actually is, traditional logic and probability theory make the exact same assumption.
They both assume the universe exists in a definite state.
Right. The patient in our clinical example either has a microscopic cavity forming in their enamel right now, or they do not. The physical matter is not in a superposition.
The reality is binary. The epistemological commitment, though what the agent actually believes about that reality, is where probability diverges.
What's fascinating here is that when an AI diagnostic system outputs probability of cavity equals 0.8, it is not making a claim about the physical tooth being 80% decayed.
Right. The point 0.8 does not exist in the physical tooth.
It exists entirely within the agent's knowledge state. It is a quantification of the agent's ignorance regarding the true physical state.
And this prevents so many systemic errors in model design. Because when an agent gathers new evidence, say a really clear X-ray, the physical tooth hasn't changed at all. But the knowledge state updates instantly.
Gathering new evidence changes the probability without contradicting the old probability. The old probability was an accurate reflection of the prior knowledge state.
And this framework applies not just to discrete states like cavities, but to continuous variables too, like predicting tomorrow's noon temperature using a probability density function, or PDF.
Continuous variables are tricky because there are infinite possible specific temperatures.
Right. If the model outputs a uniform distribution between 18 and 26 degrees Celsius, the probability of the temperature landing within any subset of that range is proportional to its width.
Which leads to a counterintuitive mathematical reality.
Yeah, the probability of the temperature being exactly 20.12 degrees is mathematically zero.
Because a specific exact numerical value on a continuous spectrum has a width of 0. It is a region of 0 width. The area under the curve for a single infinite point is 0.
It's wild to think about, but it makes sense. The probability models deal with infinite spaces by assigning non-zero probabilities only to intervals or ranges.
Because infinite precision is beyond the reach of any physical sensor or predictive model.
So we have these rigorous mathematical structures, sample spaces, density functions, axioms. But there is a massive philosophical debate lurking underneath all of this.
The debate over where probabilities actually come from.
Right. When we initialize a model and declare that the prior probability of a cavity is 0.1, what is the justification for that number? The text takes this historical and philosophical sidebar, and it is fascinating because it dictates how we train modern data models.
The debate essentially splits into three distinct epistemological camps. The first is the frequentist school.
Heavily championed in the early 20th century by figures like Richard von Mises, right?
Correct. To a frequentist, probabilities come purely from experiments. You cannot just theorize a probability. You must run the trials. The probability of an event is strictly defined as the limit of its relative frequency in a large, technically infinite number of trials.
So if you want the probability of a coin landing heads, you flip it 1,000,000 times and record the fraction. But the frequentist approach runs into a severe limitation when dealing with complex, real-world data.
The reference class problem.
Yes. If our dentist wants to determine the frequentist probability that a specific patient has a cavity, they have to consult historical data. But which data?
They must define the reference class. Do they look at the cavity frequency for all humans globally? That gives you a huge sample size, but it's practically useless for a specific demographic.
So they narrow it down. They look at patients of the exact same age, still too broad, the exact same diet, the exact same dental hygiene routine.
If they try to include the patient's weight to the nearest gram and their mother's maiden name, the reference class drops to 0.
Because no two human beings share that exact confluence of variables. There's this quote by the mathematician I.J. Good in the text that absolutely blew my mind.
Oh, about the uniqueness of events.
Yeah. He points out that every event in life is unique, and every real-life probability that we estimate in practice is that of an event that has never occurred before.
It highlights why the frequentist view struggles in dynamic AI environments. If you adhere strictly to historical trials, you can never assign a probability to anything complex.
Because the perfect reference class is always a class of one.
Which brings us to the second camp, the objectivist view.
Often associated with Karl Popper.
Right. Objectivists argue that probabilities are real, inherent physical properties of the universe, the propensities of objects. A fair coin has an intrinsic physical propensity of 0.5 to land heads, independent of our knowledge or any historical trials.
Which maps well onto quantum mechanics. Radioactive decay is objectively probabilistic at the subatomic level. But it doesn't help us build an AI to predict the stock market or diagnose a disease.
Macro-level systems are essentially deterministic. Our uncertainty in macro systems stems from our lack of data, not from quantum indeterminacy.
That realization leads us to the third camp, which is essentially the engine of modern artificial intelligence, the subjectivist or Bayesian view.
Pioneered by mathematicians like Bruno Di Finetti. This view treats probabilities purely as a characterization of an agent's beliefs.
It frees the engineer from needing infinite historical trials or trying to prove some physical propensity. A Bayesian agent is allowed to assign any prior probability it wants to an event.
Provided that the belief structure is internally consistent.
Right. But hold on, if Bayesian probability is just subjective belief, what binds it to reality? Why must we follow these math rules? What prevents an agent from assigning completely irrational numbers?
The mining agent is Kolmogorov's axioms. Andrei Kolmogorov established the foundational rules that all probability distributions must obey. And the most critical constraint on subjective belief is the inclusion-exclusion principle.
This dictates how we handle disjunctions,
Yeah,
right? Or statements.
Exactly. The probability of event A or event B happening equals the probability of A plus the probability of B minus the probability of their intersection.
You subtract the intersection, so you don't double count the instances where both occur simultaneously.
If your subjective beliefs violate Kolmogorov's axioms, you are structurally irrational, and we can mathematically prove that this irrationality will lead to systemic failure.
This is Bruno de Finetti's brilliant argument from 1931, the betting game.
The Dutch book.
Yes. He demonstrated that if an agent holds a set of subjective beliefs that violate the axioms of probability, a betting opponent can guarantee you lose money no matter what happens.
Let's walk the listener through the Dutch book example from the text.
Let's do it. Say we have Agent 1, and Agent 1 has contradictory beliefs. They believe the probability of event A is 0.4. The probability of event B is 0.3.
But they believe the probability of A or B happening is 0.8.
Right, which violates the inclusion-exclusion principle,
Right.
because 0.4 plus 0.3 is only 0.7. The disjunction cannot possibly be 0.8. Their belief in the whole is higher than the sum of its parts.
So Agent 2 comes along and sets up the stakes based on Agent 1's own stated beliefs.
Agent 2 bets 4 to 6 on A, 3 to 7 on B, and bets 2 to 8 against the disjunction. Because Agent 1's internal math doesn't sum correctly, the payout structure becomes completely unmoored from reality.
In every possible world outcome, whether A happens, B happens, both happen, or neither happens, Agent 1 loses money. They lose $1 to $11 in every single scenario.
Agent 2 essentially exploits the mathematical contradiction. And if you're listening to this, your potential objection might be, well, what if I just refuse to bet? I just won't play the game.
But refusing to bet is impossible. In life and in AI systems, every action or inaction is a bet with an outcome.
Choosing to cross the street is a bet. Outputting a medical diagnosis is a bet. Allocating computing power is a bet. If a machine learning model's internal probability weights violate Kolmogorov's axioms, the environment itself acts as the opponent constructing the Dutch book.
The environment will constantly bleed the agent's resources until the agent fails entirely.
So what does this all mean? It means we need a rigorous mathematical model to track our beliefs perfectly. We need a way to maintain absolute consistency across thousands of variables.
Which brings us to the theoretical gold standard of probabilistic inference, the full joint probability distribution.
And I see your backdrop has shifted again.
We need more space for this one.
It's a giant chalkboard now. It is completely filled with mathematical matrices and tensors. It looks like an absolute scaling nightmare.
Because it is. A full joint probability distribution is a multidimensional table that specifies a precise probability for every single possible complete assignment of values to every random variable in the domain.
Okay, let's walk through the 3-variable dentist example to visualize this. We have toothache, cavity, and catch. Catch being the dentist's little steel probe catching on the decayed enamel.
3 Boolean variables, true or false. This creates a 2 by 2 by 2 table.
So that's 8 unique possible worlds. The full joint distribution assigns a probability to all 8 of those worlds, ensuring they sum to exactly 1.
Once that table is populated, the AI essentially possesses omniscience within that specific limited domain. It can answer any query you throw at it using basic arithmetic operations.
The primary operations being marginalization and conditioning.
Let's explain marginalization first. If the AI needs to find the unconditional probability of a cavity across the entire population, it extracts the subset of worlds where cavity is true, regardless of the states of the other variables.
And it just sums their probabilities together.
Exactly. It is mathematically summing out the variables you don't care about to project the high-dimensional data onto a lower-dimensional query.
And conditioning is what you use when you receive new evidence. Say the AI observes that the patient definitely has a toothache. It restricts its view entirely to the slice of the table where toothache is true.
It discards the rest of the universe. And within that specific slice, it calculates the ratio of worlds where cavity is also true.
But doing the math for conditioning usually requires knowing the baseline probability of the evidence itself, right? Which can be annoying to track.
It can be computationally heavy. But the text introduces a brilliant shortcut here, the normalization constant.
Denoted by the symbol alpha.
Yes. Alpha allows you to calculate relative proportions and scale them to 1 without needing to know the overall probability of the evidence.
It's such a clever trick. Instead of calculating the absolute probabilities, the AI calculates the relative proportions of a cavity being true versus false within that restricted slice. Say the raw extracted numbers from the table are 0.12 for a cavity and 0.08 for no cavity.
Those aren't probabilities because they don't sum to 1.12 plus 0.08 is 0.20.
Right, but the ratio is perfectly accurate. By introducing the normalization constant alpha, the system just divides those raw numbers by their sum. It dynamically scales the relative weights back into the strict 0 to 1 pounds,
yielding a 60% probability of a cavity and 40% against.
without ever needing to query the global baseline rate of toothaches. It's so elegant. But, and this is a massive but, this method has a fatal flaw.
A curse of dimensionality.
The table size. For n Boolean variables, the table size is order 2 to the power of n.
Our 3-variable dental example requires 8 entries, but if we expand that to a realistic medical diagnostic AI analyzing just 100 symptoms and history data points,
The table is 2 to the power of 100, which is phenomenally huge. The text points out that this math is perfect, but it is completely impractical for AI to use in the real world.
2 to the power of 100 exceeds the data storage capacity of all the server farms on Earth. You cannot store it. And iterating across that table to perform marginalization would take longer than the current lifespan of the universe.
So the brute force mathematical perfection of the full joint distribution renders it useless. How do we save AI from this scaling nightmare?
We use independence.
If we can prove that certain variables do not influence each other, we can dismantle the monolithic table. Let's talk about absolute independence first. If we add a weather variable to our dental model, is it raining or sunny?
We intuitively know your dental problems do not affect the weather.
Right. And in terms of math, absolute independence means the probability of A given B is simply equal to the probability of A provides no information.
Because the weather is absolutely independent, we don't need a massive 16-entry table. We can factor the architecture. We maintain one 8-entry table for the teeth and a separate, isolated table for the weather.
But the problem is, absolute independence is incredibly rare. Almost everything in biology or economics is distantly correlated. If we demand absolute independence, we can't simplify anything.
Which is why the real lifesaver of AI is conditional independence.
Let's look at the toothache and the catch from the dental probe again.
These two variables are highly correlated. If the probe catches, there is a strong likelihood the patient has a toothache. They often happen together. They are not absolutely independent.
But their correlation is mediated by a third variable, the cavity. The cavity causes both the pain and the physical hole that traps the probe.
And here's the mathematical revelation. Given the presence of a cavity, the toothache and the catch become conditionally independent of each other.
The cavity separates them.
Yes. If the AI already knows the state of the cavity with certainty, observing that the probe caught provides 0 additional mathematical information about whether the nerve is transmitting pain.
The paired variable fully explains both children. This specific architecture is the foundation of the naive Bayes model. It allows the AI to factor the probability distribution locally.
It scales beautifully, and it is intimately tied to the most important equation in probabilistic reasoning,
Here's where it gets really interesting. Bayes' rule,
Thomas Bayes.
the crown jewel of this deep dive. Bayes' rule allows an agent to calculate a difficult conditional probability by inverting it. Posterior equals likelihood times prior, divided by evidence.
Let's walk through the meningitis example to show why this inversion is so vital.
Okay. A doctor knows a stiff neck implies meningitis 1 in 5,000 times. That is diagnostic knowledge, the probability of the disease given the symptom.
But the doctor also knows that meningitis causes a stiff neck 70% of the time. That is causal knowledge, the probability of the symptom given the disease.
Why is causal better? Let's say a sudden meningitis epidemic hits the city.
During an epidemic, the baseline prior probability of anyone having the disease spikes massively.
Meaning the old diagnostic rule of 1 in 5,000 is now entirely obsolete. It's wildly inaccurate. If an AI uses that diagnostic rule, it will underdiagnose the disease and people will die.
But the causal mechanics, how the disease physically inflames the meninges and affects the neck that remains rock solid. Whether it's an epidemic or an isolated case, the causal probability remains 70%.
This is the genius of Bayes' rule. It allows the AI to store the invariant causal knowledge and use it to compute the fragile diagnostic probability dynamically. When the epidemic hits, the AI just updates its prior probability of the disease, runs Bayes' rule, and instantly generates an accurate diagnostic probability.
The internal mechanics remain sound even as the environment radically changes.
It's just phenomenal. Okay, so we've traced the evolution from absolute logic to probability, expected utility, conditional independence, and Bayes' rule. To really synthesize all of this, we have a fantastic case study.
Surviving the Wumpus world.
And I see your backdrop has changed to a dark, pixelated labyrinth.
A cave system, yes.
The Wumpus world is a grid-based AI game. The listener is in a grid. There are hidden, bottomless pits in some of the squares. Stepping into a pit kills you instantly.
The environment is partially observable. You can only sense your immediate surroundings. Specifically, pits cause a breeze in all directly adjacent squares.
So you're moving through the dark, and you feel a breeze. Where is the pit? Let's say there are 3 unvisited adjacent squares. A purely logical agent maps the possibilities and realizes a pit in any of the 3 squares is logically consistent with the breeze.
Logic cannot tell them apart. It only knows a pit is possible in all 3.
The logical agent is stuck. It has to guess randomly, facing a massive risk of death. Now let's drop our probabilistic agent into the exact same scenario.
Every square has a 0.2 prior probability of containing a pit.
If the agent tries to use the brute force full joint distribution to calculate the odds for the whole board, say there are 12 unvisited squares, it has to calculate 2 to the power of 12 possible worlds, over 4,000 calculations.
It bogs down. But the probabilistic agent utilizes conditional independence. We divide the unvisited squares into 2 groups. The frontier, which are the squares touching our known path,
And the other squares, which are deep in the dark.
the breezes we feel right now are caused exclusively by the frontier squares. A pit in the far corner has no causal influence on our current sensor.
Which means using conditional independence, we can completely ignore the other squares. We factor them out of the math entirely to simplify the calculation.
We reduce the problem to just analyzing the valid permutations of the frontier squares.
And the result of that Bayesian calculation is incredible. The agent finds that the probability of a pit in the left square is 31%. The right square is 31%. But the central square is 86%.
Logic couldn't differentiate them. But probability theory, synthesizing the priors and the evidence, reveals the central square is almost certainly a death trap.
The AI roots around it, minimizing risk, maximizing utility, and survives. It gives the AI the exact path to survival.
If we connect this to the bigger picture, the journey from the rigid limitations of absolute logic to the fluid, powerful mechanics of probability and Bayes' rule is profound.
It really is. We want to thank you, the learner, for embarking on this deep dive into the source material. Mastering uncertainty isn't just for AI, it's the mathematical foundation of everyday human rationality.
These mathematical pioneers, Pascal, Laplace, Bayes, Kolmogorov, they built the bridge that modern AI walks across today.
They give us the tools to navigate a chaotic universe. But before we go, I want to leave you with a final provocative thought, going back to the reference class problem.
I.J. Good's observation.
Right. If every event in the universe is truly unique, and no 2 contexts are ever perfectly identical, then there is no objective frequency to anything.
We are always grouping unique things together just to make the math work.
Exactly. So is probability actually a fundamental property of the physical universe? Or is probability just the most successful, most mathematically rigorous illusion the human mind ever invented to cope with its own ignorance?
That is the question.
Think about that the next time a model tells you what's likely to happen. We'll catch you next time.